To start with Gaussian elimination, we will introduce the row echelon form. A linear system is said to be in row echelon form if in every equation at least one variable is present that is not represented by any following equations. Like here. Here we have z, here we have y and z, and here we have all three unknown variables. So this is an example of system in row echelon form. We can solve it by starting with the last equation. Each equation is solved and its solution substituted to the equation above. So, for example, we take number 3 here and we solve it for z. So, z will equal to 3. And if we take the second and put y plus 4 multiplied by 3 equals to 11. And we will get y equal to minus 1. And now we know two variables already, and we can put them on the first equation, which is minus x plus 2 multiplied to minus 1 plus 3 multiplied by 3 equals to 5. And here we have minus 2, and here we have 9. And in the end, and x will be equal to 2. So the solution set for this system will be x, y, and z. So this is clear. This method, when you solve it backwards, called back substitution method. How to solve the system with a row echelon form is easy. Main problem here is how to bring the system into this form. So we can do it by making different manipulations to the equations. For example, what we can do? We can exchange the equations, we can swap them, and we can multiply with any non-zero number. And also we can do addition or subtraction of one or multiple rows in a form. So let's bring this system into the row echelon form together. So the first equation, we can just leave it as it is. It's fine for us. So we will just leave it like that. And for the second equation, if you look here, we can add first and second equation here. Thus, we will remove this variable. And for this one here, we can add the first equation multiplied by 2. And it will also help us to eliminate x from here. So let's just go on, and after the first manipulations, first equation will remain the same. We will not do anything with that. We just leave it. It has 3 elements, and second one needs to have 2 elements. So we need to remove the x. And the second one, we add these two together, 1 and 2. Then we will get rid of x. Then we will get y plus 4z equals to 11. Here it's clear. Okay, then we add to the last third one 2 times multiplied first equation. That will give us, so we get rid of x here. Here we will have minus 3y plus 4y, which will give us y. And here we have minus 4z. And here we will have 6z. And 6z minus 4 will give us 2z. And minus 5 plus 10 will be 5. All right, so let's have a look one more time. So we have here, so the first one and the second one already in a row echelon form. And we need to do some manipulation on the third so that we get rid of this variable y. So what we can do, we can subtract from this equation the second equation. And this way we will get rid of y. So we can rewrite this in a new form. We can rewrite it as following. We leave the first, so it will be minus x plus 2y plus 3z equals to 5, and then y plus 4z equals to 11. And the third one here, this one minus second one will give us, we get rid of y, 2z minus 4z will give us minus 2z, and 5 minus 11 will give us minus 6. So if we look closely, now we got this system here looks exactly like this one. And this system can be solved using back substitution method, explained earlier. So the whole process of bringing system first into the row echelon form and then further solving it by back substitution is called Gaussian elimination. As in previous examples, there are situations when dealing with Gaussian elimination, we come up with systems which are unsolvable or contradicting. This is what we are going to look next. So let's have a look on the following system. So this equation is okay for row echelon form. This one is also. And for this one, we need to get rid of 2y. How to get rid of 2y? It's very obvious here. We can also subtract the second equation from the third. So let's do that. So we will leave first 2 without any changes. Plus z equals to 3. And 2y plus 3z equals to 5. So the third one, we will subtract from the third equation the second. 2y minus 2y will be 0. 3z minus 3z will be 0 as well. Wow. And then 4 minus 5 will be minus 1. So this here is contradictory. That's why we have no solution here. So it means that our solution set is empty. Next example is this one. So the first is in row echelon form, second one as well. And we need to work on the third one. What we can do, we can also subtract the second equation from the third. So let's do that. So it will give us x plus y plus z equals 3. And second equation where we have y plus 2z equals to 3. And here, when we subtract from the third the second equation, we will have 0. And if we look again, we can just immediately see here that these two equations are similar. And we can just remove one of them and use only these two. And we can introduce a real parameter t instead of z. So we will introduce parameter t and replace it with z. So for example, we write the second equation as y plus 2t equals to 3. And we solve it for y. 3 minus 2t. And then we take the first equation and solve it for x. So t is equals to z and y is equals to 3 minus 2t. And now we can put it back into the first equation. So it will give us x plus y is 3 minus 2t, and z is equals to t plus t equals to 3. So now we can find out that x is equal to t. And the solution set for this system will be t 3 minus 2t, and z is also equals to t. So this will be our solution set. And thus we have infinitely many solutions. T is any real number. So this is basically it for the echelon form. It's not that complicated. The only thing that you have to be very careful while you're dealing with these manipulations. The last part of this chapter, I want to show you one more type of linear system that you can come up with. These are parametric linear systems. So linear system of equation can also depend on single or multiple parameters. In such cases, the solution set depends on the values of the parameters. So we also saw in the previous examples that we can include some parameters like t, we included that parameter, but here they already included in our system by default. So for example, here we have parameter alpha. So in equations that contain parameters, we try to eliminate as many variables as possible. For example, we can also leave the first one like that. From the second one, we can subtract the first one and get rid of x. And the third one, we can add the first equation, then we will also get rid of x and y as well. Let's do our manipulations, and we will have here the same equation. Second equation, we add first and the second one, so we get rid of 2x. We get rid of y as well, and 5z minus 4z will give us z equals to 1 minus minus 2, which just give us plus, will be 3. And this was the second equation. And the third one will give us the following. So we here add the first one. This will be cancelled, and minus 6z plus 4z will have minus 2z equals to minus 4 plus alpha. So here we can't go further. We can add here the second equation but multiplied by 2. So let's have a look what we get in the end. So we will leave the first equation as it is, minus 2x plus y plus 4z equals to minus 2. Z is equals to 3 here, and here we have 0, and here we will have 2 plus alpha. So here we will have two situations. So if alpha is equal to minus 2, when alpha is equal to minus 2, then we will have no contradiction and 0 equals to 0. And it holds. Then we will have a solution, but the solution will not be unique. Then, like in the previous example, we will have to introduce a new parameter. For example, we will introduce, instead of y, new parameter t, and then z is equals to 3. And then on the first equation, we will substitute it minus 2x plus y, which is t, plus 4z, which is 4 multiplied by 3, equals to minus 2. So here we will solve for x following. So we move t to the other side, then we will have 12 here. 12 on the other side will give us minus 12 minus 2 will be minus 14. And then if we divide everything by minus 2, we will get half t plus 7. And for that, our solution set will include half t plus 7, t, and 3. So this is our solution set when alpha is equal to minus 2. There's the second situation when alpha is not equal to minus 2. In this case, this will be contradictory. We will not get 0 on the both sides, and thus solution set will be empty. It will be unsolvable. That's it for our chapter 5, where we revised linear system of equation and revised different methods how we can solve them. And see you in the next chapter, which is chapter 6, where we will look into the functions. Have a great day and see you next time.